In this video, I'm interested in doing a little comparison between two different techniques for how to find dz dt in this case. We've been given that z is a function of two variables being x and y, where x and y are both parameterized in terms of t. Now, my personal interpretation of this is that really what we're saying is that x and t are defined in terms of a vector function, and that vector function is the square root of t comma 1 over t. And we're taking these parameterizations and dealing with this function of three variables. Regardless, I wanted to show off two different techniques for how to find this. First one is going to be using the brand spanking new chain rule that we introduced in our last video. Now, with the chain rule, I would strongly recommend that you create yourself a tree diagram in this case so that we can figure out what our total derivative for z is going to look like. So this will be dz dt is equal to, we can go from z to x and x to t. So that's a partial derivative of z with respect to x, but an ordinary derivative of x with respect to t. Now, partial derivative for z because z is a function of two variables, ordinary derivative for x because x is a function of only one variable. Now, the other way we can go from z to t is from z to y and y to t. So partial of z with respect to y times dy over dt. Now that does, however, mean that we do have four derivatives to take here. Thankfully, those derivatives aren't too bad. For the partial of z with respect to x, we'll be differentiating the sine of x, treating cosine of y as though it's a constant. So this will be the cosine of x times the cosine of y times dx dt. Treating that as t to the 1/2 power, we'll get 1/2 times t raised to the negative 1/2 power. Plus partial of z with respect to y, this time we'll be treating cosine of y as though it's our variable and treating sine of x as though it's a constant. So that'll be sine of x times the negative sine of y times the derivative of y with respect to t. We'll call that t to the negative 1 power and apply the power rule. Negative t to the negative 2 power. So the individual derivatives aren't too tricky. Additionally, if we wanted to try to clean this up a little bit, we could put the 1/2 in front, cosine of x, then cosine of y, then times t to the negative 1/2 power. Here we have two negatives that are canceling each other out, so we could call this plus, sine of x times the sine of y all over t squared. That's a weird looking y. Or, whatever algebraic manipulations you wanted to make to it. The alternative, and I do want to show you both of these because ultimately it's going to be up to you to decide which one you want to do. So the alternative would be substitute x and y into your z function. That is to say, rather than referring to this as the sine of x times the cosine of y, we'll just go ahead and plug in what x and y are equal to. So this will be the sine of the square root of t times the cosine of 1 over t. Now technically this would be a derivative of z, this is now z as a function of only one variable, and this essentially becomes a rather complicated Calc 1 problem. So dz dt will be equal to, first off we have a product combined with our chain rules, so we'll call this first times the derivative of the second plus the second times the derivative of the first. Now each of the derivatives that we still have here is going to require the use of the chain rule. So we'll call this sine of the square root of t times derivative of the cosine function is the negative sine function. And then the chain rule says multiply by the derivative of the inside. Once again, referring to that as t to the negative 1 power, we can call that negative t to the negative 2 power. Plus the cosine of 1 over t times derivative of the sine function would be the cosine function. And treating that t, square root of t as t to the 1/2 power, we'll get 1/2 times t to the negative 1/2 power. If we pause there for just a moment and compare it to our previous result, we have essentially what's going on in this line directly. Here we have a sine of the square root of t, that was sine of x, times the negative sine of 1 over t, which is the sine of y, times the derivative of y with respect to t. And here's a cosine of y, cosine of x times dx dt. Cosine y, cosine x times that derivative. So ultimately, we're going to be getting the same result either way. In the first one, though, we have something in terms of 3 variables, and in the second case, we have something in terms of only 1 variable. I will leave it up to you to decide which way you like better, which one you want to implement more regularly. For these more basic cases, like z is a function of 2 variables, and each of those variables is a function of 1 variable, sometimes you might consider doing a substitution and going with that. We are going to see some more complicated cases, though, where you wouldn't necessarily want to do that.